2522, 500 years from where we currently stand. Almost every science fiction story this far in the future features some sort of expansive human society. But will our descendants actually live to spread to the stars? Look, there is no doubt that technological progress will continue to expand and grow, but will humans as a species also adapt to the new challenges that await us? Will the slow and random process of evolution even allow humans to live in the destitute emptiness and landscapes that lie beyond our atmosphere? Or will natural evolution prove too slow in the race against our own development? To be stuck as prisoners to our own planet would mean eventual decline or starvation at the hands of finite resources. Today, we are joined by Dr. Christopher Mason, the author of The Next 500 Years, to discuss these questions and to find out what humans need to do to survive in the next 500 years. Hello, everyone. I'm Nick Saba.
And I'm Dominic Tanzillo.
We're excited for you all to join us in the first episode of our Space Medicine podcast. Welcome to Spherical Cows.
Hello and welcome everyone. Nick, we have a very special guest today.
I see that. I'm really excited.
Yes, we have Dr. Christopher Mason with us here. Dr. Mason, we're very excited to crack open a conversation talking about the science of your new book, The Next 500 Years, including some of your previous work that's featured in the beginning of the book.
Great. Yeah. Well, pleasure to be here. Thanks for having me.
Yeah, so for the audience, Dr. Mason is a professor of genomics, physiology, and biophysics at Weill Cornell Medicine, and also the director of the World Quant Initiative for Quantitative Prediction. With the recent launch of the Inspiration4 mission, Dr. Mason has established a biobank with SpaceX to research the effects of spaceflight on human physiology.
And in fact, we rescheduled this recording around that Inspiration4 launch, which I understand you got to see live. How was that? And before we even crack into the book, how was that experience?
It was really phenomenal, actually. On the top 10 things I've ever seen in my whole life, including watching my daughter be born, it's up there because it really is extraordinary to see, the rocket essentially, because of course light moves faster than sound. So you see the light, but then the sound moves faster through solid, like the ground, than it does move through the air. So you see the light first with your eyes, you feel the rocket with your feet, and then you hear it with your ears. So it's like a trimodal experience, and you can kind of hear the atmosphere crackling, and it feels like it's ripping. And it really was beautiful and extraordinary, and also fun because I knew the crew, and we'd just gotten blood from them. So I was glad to see they made it okay.
So I have to ask then, how long have you been interested in space?
Since I was a kid, I'd say. I went to space camp when I was a kid, twice actually, and so I've always thought about either being an astronaut or a paleontologist. I guess when I was a kid, those were my two dreams. And then when I got older, so I kind of had a science and space vibe growing up. And then when I actually learned about genetics, I knew I didn't just want to do bones and think about old dinosaurs, because I think every kid just loves dinosaurs. But I actually became fascinated with the fact that the instruction set for the synthesis of every cell in our bodies in that very first cell. And I just was and still am fascinated, like, how does that happen? How do we so exquisitely control the manifestation of every cell type and what happens and how you respond to food and stress and stimuli? So I really got fascinated by genetics, and that hasn't ended. And then the fascination with space just stayed with me. So I actually, one of the first things I wrote when I started my lab was a proposal to NASA to say we should start doing space genomics. And at the time they said, well, we don't have any really samples banked yet for this, but hang on, we should have an announcement soon. And that was the twin study announcement. They were taking applications for ideas. So, and then we were selected for that study.
Yeah. So I imagine being one of the first people to, you were on the leading team that worked with Oxford NanoPore technologies in space, right?
Yep. It was part of the mission that basically said it was kind of a crazy year, because 2015 is when we had samples coming back from the space station, and we had reagents going up to the space station to do what's called the NanoPore sequencing, this little tiny small device that fits in the palm of your hand that does sequencing and does essentially lets you characterize thousands and thousands of molecules per second of what is DNA or RNA. So we showed for the first time that you can sequence in space and analyze the data and use it in theory for real-time mapping of pathogens or health on flight.
So that must have been like a dream come true then, right?
Yeah,
Like everything was building up to
it was
that.
all happening with space, and it was genomics. It was all happening. Actually, we did a Reddit with NASA and some of the other PIs on that mission. And I never forget, one of the people on Reddit, just in the Q&A and ask me anything Reddit, he said, "How does it feel to have the coolest job ever?" And I actually was thinking, like, I'm very fortunate. It's a pretty cool job. It was great.
That's incredible. Yeah.
Yeah. And that actually was one of the first framing stories in your book. The everything just coming together perfectly to get the NanoPore first on board on the Vomit Comet to test to make sure, hey, does this even have a shot of working in a weightless scenario? And then this really sets up, I think, one of the reoccurring themes throughout the whole book, which is, of course, we have a growing biological toolkit at our disposal, and this could be the beginning of a series of hopeful revolutions.
Yep. Yeah, absolutely. I think there's at one point later in the book, I called it these twin engines of discovery, where we can see the discovery of new exoplanets continually increasing, and the discovery of new genes and new species and new functions of the genetic code in all organisms is increasing at a super exponential pace. So now every day is really the best day ever to be doing science in all these fields.
So just for reference, this is your book, The Next 500 Years, which, at least in my mind, was kind of your thesis for what humanity should focus on in especially biological research in order to become a spacefaring civilization, right? Could
Absolutely.
you maybe tell us what motivated you to put together this? I mean, it's a very incredible review kind of thesis. What started all of that?
It really came from, I've always been a humanist since I read old work by Isaac Asimov and have read a lot of philosophy. So I'm a big fan of humans. Some people do not like humans. Some people think, oh, the world would be better if all the humans were dead. They're misanthropes. There are people who are not of the same ilk. But I am a humanist. I see a lot of hope and promise for our species. In particular in the book, as I describe it early in the book, is that because we do amazing things. There's music and there's art and poetry and science and there's all this imagination and all these things we've built in architecture. There's bad things, of course. There's murder and theft and genocide. There's a lot of things that we did bad, but writ large, there's a lot I find that's really extraordinary and exemplary about the human species. But one thing in particular that is, to we know, unique in the universe is the ability for humans to not just think and be cognitively aware, but actually to have an awareness of future planning so far that you can think of extinction, that you can understand extinction, and that awareness of it, as I describe, is something I've just thought about for a long time. That we are the only ones that can understand it, that can fathom it, and therefore the only ones that can prevent extinction. We can also, of course, cause it. Like I said before, we don't always do a great job of being stewards of the earth or other species, but we're the only ones that can actually prevent it or even resurrect the woolly mammoth, for example. I talk about. Could even correct our genetic wrongs of the past because of the tools of technology that have just come up in the past 20 years. So it's a really extraordinary time. And with that as a backdrop, I started my lab at Cornell in 2010, and we had one of our first iGEM teams, which is the International Genetically Engineered Machines Competition. I don't know if people have heard of iGEM in the audience, but it's basically a contest. You say, I want to make a new genetically engineered machine, which is usually a cell like E. coli or a human cell that does something. I want to take a genetic trait of some kind, whether you want to make the smell of bananas or have your cells smell like paprika or peppercorn. You can actually make your cells that in your dish smell like a lot of things. And but what we did for our, go ahead. Was that the?
Is it usually smells?
Oh no, usually they don't smell, but you can add smells. You can
Okay.
create the synthesis pathways and put them into E. coli. So if you want to make your E. coli smell like bananas, you can make that happen. But what I decided to do is we got a team of graduates and undergraduates together, and I said, okay, some point I really think we should go to Mars because I'm looking at about us becoming an interplanetary species. But to do that, we'll need to understand risk of radiation and take lessons from creatures that we know that can survive a lot of radiation, including Deinococcus radiodurans, which is an extremophile that often grows in the cooling waters of nuclear power plants or really high radiation environments like the space station. So I said, all right, let's do a comparative genomics project and try and engineer it to be even more radiation resistant as the summer project. And then as we were planning it, I typed out the 10-phase plan for the laboratory and said, here's what we should do for the next 500 years. Just as it's like a lot of things that just started on like a bar napkin, and fleshed it out and then posted it on the wiki, because every team for iGEM every year they get a wiki page to say, what are you doing? What do your experiments look like? And then they freeze the wiki once the competition starts. So it's been up there since 2011 online, and then actually one of the editors at MIT Press saw it and said, hey, I saw your 500-year plan. Do you ever want to write a book about that? And I said, well, sure. I guess I probably should. I've got a lot of ideas. But along the way, a lot of it came true, actually. So it was really extraordinary to see how quickly the science advanced, much faster than I thought it would have even 10 years ago. So that was the genesis of the 500-year plan, was just thinking, okay, if we're doing this in the next 10 years, what will we do after that? And then what comes when we go farther out into the solar system and other suns? And so it was just a quick, late night writing of ideas that then became fleshed out into a book. Once I got approached by an editor who said, this could be a book. So I said, sure, but I don't have much time. So I started just getting up at 4 a.m. and writing for 2 hours a day for most days for about 3 months to finish it up.
Well, and that's especially impressive because of how busy your lab has been in just the last year and a half with the global pandemic that's occurring. I mean, just some incredible papers coming out, the spatial genetics, genomics, and biology toolkits that your lab has been, playing with and defining. It's quite incredible, first of all. But then on top of that, you probably are busier now than ever. And so finding time to write this book probably wasn't that easy.
I just had to get up before everyone woke up, and my wife and daughter would still be sleeping. So I'd get up. I just said, it's one of those things where if there's a clear deadline, and I also had a sense of, I really wanted to get it out. I feel like it was as if there were all these thoughts in my head that if I were to get hit by a bus would be lost forever. So there was a sense of urgency almost, where I felt like if I didn't put this down, it might be lost forever. Which I gave a TED talk in 2015 that kind of talked about this a little bit, and I felt like a little bit of relief after that talk, because I felt like I had synthesized my core beliefs in 20 minutes. But of course, that's not the same as a treatise that's a full, several hundred pages. But there was a sense of a drive that I really want to craft this vision and inspire people to think ahead and get them to think about what can be possible and what should be done. And actually, as an ethical question, what our duty is. So that was part of the driving factor for sure.
And part of those ethics, I think anyone reading this book is going to come away with the term deontogenic. Let me re-say that. People are going to come away with deontogenic ethics. It's a word that populates this and really frames this whole book. Do you mind just explaining that? What someone should be coming away with what it looks like?
Yeah, so I made an entirely new ethical system. Why not? It's my book. I can write whatever I wanted, right? So I decided, and I studied philosophy a lot in college and a bit in grad school, and there's always been this battle in ethics of, well, how do you know what's the right thing to do? And so I think people, even when we're kids, we're often told, like, well, don't steal a candy bar, because what if everyone stole a candy bar? Then there'd be no candy bars, right? We get some of this early on, and that's a Kantian categorical imperative. Immanuel Kant wrote about that. So I've always liked Kant. I've read a lot of Kant books. They're in my lab. And then that's often competing against utilitarian ethics, like what is the greatest good for the greatest number, by Mill or others who've written about, this idea of like, how do you quantify the value and the good that people can do based on sort of the average happiness writ large. And Derek Parfit is a more modern philosopher who's written about that. So with that in mind, though, I was always dissatisfied because they seemed like they're at odds with each other. But I also felt this nagging sense that there's something that precedes those two. There is, before any of that has to happen, you have to existence precedes the essence of anything. Is kind of what I was saying, is that without that you can't actually do anything. You can't have any ethical system if you're not alive. So I kind of suppose that there is a framework that is ahead of everything that you might do, which is just frankly to survive. But how do you survive? You basically have to have a framework where you think about, what is my duty genetically, right? Sort of the ontogenics is sort of the study of what your duty is. The deontogenics and the genic part is the gene. Like, so what is my genetic duty, and how do you build an ethical framework around that? And the duty, if you think about it, is the simplest duty is just to survive. But then if you understand extinction, and humans uniquely do, we also can serve as caretakers and guardians, really shepherds of not only ourselves, because that's selfish. It's good to be alive because then you can do things, but also we understand the frailty of life and can actually, protect it. So I view this as a duty for our species that I propose that we should all, basically nucleate around and then enact. Yeah, but I did make up the word. It's an entirely new word, entirely new ethical framework, but it's what I really fervently believe is something we can do and should do.
Yeah, and of course, you bring all of this into play and all of this philosophy about this moral imperative,
Yeah.
because, I mean, honestly, what you are suggesting in your novel, being genetically engineering humans themselves in order to survive better in these environments, it is quite controversial, right? At least today, with what has happened in recent history.
Hmm.
So I did want to ask you, and this might be a bit of a challenge, but if you could just elevator pitch, if you met someone in an elevator, like you met Dominic or I in an elevator, and we said, why should we start genetically engineering humans? And you just had like the span of an elevator ride to try to convince us.
Right.
What would you say? Like, what would you say to the common person to kind of get that drive, that rally to invest in this science?
Easy. I'd say this may be our only chance at surviving. And if you value anything in life, whether it's your family, music, poetry, science, religion, anything that you value needs to have us exist for you to continue to value it. And we're not built to survive on other planets. We're not built to last there, but we could be. And maybe we'll get lucky. There's kind of a good luck plan for humanity. We like send people there and say, hopefully we'll survive. But there's a much more ethical plan, which is let's protect people as many ways as we can who are being sent to these dangerous worlds, pharmacologically, physically, and even genetically. That would be in a
Yeah.
nutshell.
So
We got to the 10th floor, and I'd say that's it. Yeah.
I don't necessarily want to play devil's advocate, but I do have to ask you talk a lot about genetically engineering other species, other organisms that aren't necessarily humans. And at one point, you do talk about engineering the microbiome,
Yep.
or talking a lot about studying epigenetics and finding ways to engineer that. Do you
Absolutely.
think either of those, or a combination of being able to engineer those aspects of being a human, would give enough protection where it wouldn't be necessary to fully genetically engineer a person? Or do you think that that is an inevitable step for humanity?
I don't think it's inevitable. I think it is the epigenetic editing, the microbiome modifications, even other metabolomic profiling, or borrowing tools and lessons, and even proteins, purified proteins. Like right now, we purify proteins as therapeutics all the time, and say we just grow them in large vats and infuse them into people, and those are therapeutics. So if we are lucky, we'll be able to get away with some of the things that are portable, that can be lyophilized and like dried down, and then you can use them as a therapeutic rather than germline genetic engineering. So I think it is the most severe way to ensure survival in terms of a disruptive plan, but it is the way that is the most permanent. And when you go to a resource limited setting where you won't have access to large scale manufacturing of pharmaceuticals or huge industry, it may in some cases be the only way to survive long term. But it's definitely not the only way ahead. But the controversy in the book, which I do on purpose, is to think, well, what if this is the only way that we're going to be able to make it?
Mm,
And what if we know, it's fine now, but in a billion years from now, when the sun starts to boil the oceans and we haven't figured out a way to do it with those other means, we may have to consider some of these more drastic measures of engineering.
gotcha. Gotcha. And it's better to start that now, of course, than too far
Yeah.
down the line.
Or I'd say tinkering and cell, like we do with most medicines, with most clinical trials. We start small. We do things in first in
Mm,
cell lines, then a little bit maybe in a mouse model. Then you start a clinical trial with only a handful of people to make sure that it's safe, and then you test for toxicity and broader efficacy, and then you do a phase 3 clinical trial and make sure it really works. And the same thing would be true here in terms of safety and efficacy. But I add in the book and talk a lot about, I think because it's such a severe change, I would actually say this would comprise a new kind of clinical trial that should span multiple generations to
gotcha.
make sure that we didn't miss something, because it is such a drastic move and such a drastic measure. I'm not naive to think, well, what if we missed something, or what if we've modified one thing, but then two other things over here changed? So I propose that some of these trials should be, multiple generations before we could really declare a safety. Efficacy would probably tell right away, but safety I would want to see over generations.
And so, following that, I do have to ask, with all of this kind of kicking off, um, with the CCR5 mutations and the two attempted genetically engineered children, in China, does that kind of come off a little bit as almost a Chernobyl event for genetically engineering? Is it something that might dampen the field for a long time, as
It
with
yeah.
nuclear engineering?
Spot on. It could, and it did, and I think it still has, because Jen he is in jail right now for what he did. But what's interesting is it really demonstrated the foolishness of our knowledge of genetics today, and what because what he did is the deletion you mentioned is there's something called the CCR5, which is a cytokine receptor locus that's on T cells, which is how HIV can get into the cell and start to kill the cells. And the idea was that there are people who have been born, like this guy who was born in Berlin called the Berlin patient, who had a deletion in that gene, 12 base pairs gone, that made it so that HIV couldn't get in. And actually, almost no strain of HIV can get into your T cells if you have that mutation. So, what the Chinese researchers did is say, well, okay, well, if there's parents who have HIV and they want to make sure their kids never have to suffer from HIV or worrying about it, let's genetically engineer the embryos to create the same sort of a bonus, the same idea of I have this kind of genetic superpower where I cannot get HIV. And on the surface, that sounds like, well, that's not, that sounds like a laudable idea. Let's prevent disease before it can even happen. Except that one of the key words I talk about in the book a lot is pleiotropy, which just means one gene can have two or more impacts and functions and dynamics inside the cells. And in this case, if you have a CCR5 deletion, you're actually more likely to get West Nile virus than people who don't. So you might decrease risk for one disease, but then you could increase it for another. And this is true, for example, for like sickle cell disease, where you can decrease risk of malaria, but increase risk of clotting. So like most things in biology, it's a very careful balance between the benefits and the risks and the pros and the cons. But what he did really set the field and made everyone aghast, because he didn't really inform the parents in great detail. He didn't really
Well,
think about the nuance of genetics, and then
he lied
and
to
he
the
did it,
IRB, right?
yeah,
As well.
and kind of
Yeah.
doctored it and did it in secret. And if you're really going to start to do whole genome synthesis or genome engineering at that scale, it should be with public engagement. It should be with very clear goals. It should be done. You start maybe with just one couple. He did several couples. He enrolled, and some of that's because that's normally what you do for a clinical trial. But for something like this, you should be much more transparent. And then also the CRISPR editing methods that he was using were some of the very first kind, which are not that good, frankly. Like you try to edit one site, you edit these what are called off-target sites, sometimes dozens or hundreds of other sites. There are newer versions called like prime editing from David Liu and others that are much better. And I think the field will get better. But there's even new genome editing systems, Omega systems, just discovered last month from Feng Cheng, that are even better potentially. So, I think we're still in this very early stage of discovery, which I put in the book. That'll be the next 20 years that we'll still have to do that before. Like, I don't propose any astronaut studies of genome engineering till 2040 or 2050, basically, because I think we still have 20 years to go on just basic knowledge, which is an exciting time, though. It's wonderful, but we have a ways to go before I think we should do any experiments like that.
And as we're doing the groundwork, one of the other ideas that I think people reading the book might have to warm up to and come away with is the idea of the metaspecies.
Mm-hmm.
So let's say we do take these more drastic steps of not just editing our epigenetic profiles or microbiomes, but we actually start moving towards genetically engineering humans. How does that play in with the idea of the metaspecies of life even?
That's a good question, and I struggled with what to call it in the book. At some point, I called it the holobiont. Some people call it that. I call it the metaspecies, just because I didn't quite like the word holobiont as much. But the idea is, when you modify one thing, you may modify other creatures or interact with them in different ways, and then eventually, we should think about changing entire ecosystems, because we actually do this accidentally today. We think about large-scale release of pesticides, chemicals, byproducts of industry. We just put them into like rivers and streams, sometimes treated, sometimes not. And that's creating large-scale ecological changes that we're not really sure what they're doing, but we're doing it anyway. And the EPA regulates it as best they can, but it is, it's something we're doing now, but we're not doing it with volition. We're doing lots of accidental engineering, or even the buildings in which we live and work have their own microbiome on their ceilings and their walls, and there's mold in different places. And it's all kind of by accident. No one really takes action unless someone starts to get sick or you see black mold on your walls. But there is an ecosystem in every room, in every building, in every house, and it's accidentally designed. What we could start to do, though, and I think actually have to do eventually, is purposeful design and actually ensuring that we're having the good ecosystems around us. So it's the walls, it's our skin, it's the forest, it's the really every part of the biome.
Well, and we'll move off of ethics at some point, but I also wanted to talk about you address some of the common counter arguments, not just towards genetic engineering, but space travel writ large. The whole some people, and this is just me. Some people like it just makes sense, and they're like, oh, of course we got to explore the stars, and other people are like, well, maybe not, right? And it's just sometimes it just depends on personality. One of the most compelling ones that I hear often thrown out and you address is the idea of other priorities existing out there, that there are more items of higher demand. And of course, your work and many other ones show that, well, this might not be an either or type situation. I'm not sure if you're able to add a little bit more on that.
Yeah, that's spot on. I mean, we can walk and chew gum at the same time. We passed the Civil Rights Act in the '60s and went to the moon in the United States. We even in my own lab, I've managed to publish a book and launch people into space and participate in missions while creating 4 different COVID diagnostics and sequencing patients as they come in. So we know you can do both things at the same time, even as one person, right? So I think this is, and it doesn't really take away from the other priorities. You can have a lot of, it's not as if we only have $100 and we have to figure out what we're going to do with it. It's trillions and trillions of dollars that the U.S. has alone to address systemic economic problems, racism, poverty, other challenges in society. And we can do, even the discussion now is a $3 trillion aid package that'll probably come down. But, if we were looking at a very, very scant funds and really having to pick, it would be a different conversation. But the scale at which these problems need to be addressed are international. And the budgets of NASA are just really, they're not like they used to be, where it's 5% of the GDP, like in the '60s. But even then, we actually made a fair amount of social progress, as well as other progress in other parts of society. So so that's an easy one, I think, to refute. The hardest one I have is when people say, well, I just don't care. Some people really, literally just don't care. And to that, I say it's very much like a suicide. When people want to commit suicide, in this case, inaction is itself a suicide for our species. If we just keep doing nothing and keep doing nothing, eventually we literally won't have a planet left. And so, you could say we've got time. We have probably 1 billion years before the sun boils off the oceans. We've got some time, but that's assuming we don't have, say, a global pandemic again. That would be worse, or an asteroid hits us. And so I think there is a false sense of inaction that seems reasonable. But actually, I would say we can consistently make progress on all these fronts at the same time.
And investing in biotechnology in some ways can address both those at the same time, right? That, small investments now can have immediate payoffs, right? We're not choosing exclusively 1,000 years in the future, 500 years in the future. No, it can have really now present benefits. At the same time, that's also addressing the person who might not care. Well, in your lifetime, we can see, benefits of biotechnology improve healthcare quality and life care. For everyone, including you.
Yeah, and even even the getting sequencing working in space. People say, "Wow, do you have to do that? What's this flashy way to put a genomics project in space?" But that's how you do remote monitoring of pathogens. The call I just came from the Rockefeller Foundation is to deploy that exact system with low resource settings, with limited materials, and to do sequencing literally anywhere, and then upload it to satellite systems that are put up by SpaceX that are in remote areas that then can survey the data. So you have a true sort of emerging pathogen network at a global scale. And so, there definitely is a virtuous cycle between the two disciplines.
Yeah. So as technology is increasing because of this field and fields like it, you have these kind of stages of this plan that you lay out in the next 500 years. And I do want to get into specifically what those stages are, and I want to hear what influenced you to kind of segment off these different steps for humanity. But I think one of the most interesting things that I found was that you say it'll take about 100 years to settle on a moon such as Titan after we make our initial visit. And it's interesting to me that you make this comparison and that we're seeing that you say that, because we have landed on the moon over 50 years ago. It was,
Did it
yes.
9 times, yeah, and
Yeah.
almost, but the first time was about 50 years ago, and now then we did it 8 more times after, and
Yeah.
but 50 years have passed, and
50 years have passed, and we don't really see much support. I mean, NASA's starting to get there. They have said multiple times that they want that to be a goal, to land and settle on the moon and make a colony. But there's really not that much development, I think, as far as public knowledge goes, going on that front. Do you expect that to become exponentially greater in the next 50 years, especially when we're, colonizing celestial bodies other than the moon?
I think, well, actually, I know it's already moving at an exponential pace in terms of the number of objects launched into space. It's one of the figures in the book. And I think that, yeah, I mean, it definitely is a lot to complain about that. Why is it since 1973 all the way through really the late 2010s, we did almost nothing with the moon, no real plans, a lot of lip service. But I think more things have been launched in space than ever before last year. More countries have visited the moon and Mars than ever before in the past 10 years. And I think capacity has changed. It used, in the 60s, there were only two countries that could maybe get to the moon, and only one did. But now there's actually multiple private sector entities, multiple governments that can do it and are planning it. And architects, you literally today you can have a job as a lunar architect, or people making habitats that should go there in about 2 years. Now, we'll see. Maybe in 5 years, we're all like, what happened? Where did they go? But if all goes according to plan, there will actually be lunar habitats with people living on them in about 3 to 4 years, and being built, though, in 2 years, 2 or 3 years, which is not that far away. So I think it took a while, because the first trips to the moon were like, holy crap, we were just amazed that we got there. And that was enough. But to actually live somewhere takes a bit longer, and it takes a scale up in capacity, I think. And for a little while, it was also for the Cold War. We went there not because we really wanted to stay there. It was just to say, aha, we got there. So, but now I think, but to that point, though, of why not more, is it's still really expensive to get there. There's no real reason you need to manufacture something in space or on the moon. There's some rare metals there, maybe a little bit, but there's very little water. There's really not much there. We're going there to in a very expensive way, build a base camp that we won't bring much back. I mean, you can do a lot of geology and study the history of the solar system and cool science, but it's not like a lot of what drives people in capitalistic societies are ways to make money. So there's not much ways to make money yet from that. So I think that's part of the challenge too.
So I want to transition on and talk about these different stages that you have, because you have the now, you have the near future, or I guess you'd say the next 20 years after now. And then you kind of start to slowly fan out until you get to, it goes in chunks of
50 to 100 years.
50 to 100 years, right? So how did you kind of segment these off? What was the big steps for each one, if you recall off of the top of your head?
So it gets a little bit more vague as you get farther into the book, of course, because what do I know what 300 years from now will look like? I have to guess a little bit. But whereas the next 20 years, I have a pretty good sense of trajectories of different fields of medicine and science. So it's based on a little bit of where I can make some of the more concrete claims. And it's also just based on, I think, everything that we would need to know and learn about and build in stages to then be able to get to planets that are farther. So when we get to farther and farther away from the sun and from our planet, we'll need more extremophiles. So those show up more in the latter chapters of the book, is because we'll need evolutionary lessons from all creatures, not just even our own cells, but anything that's ever survived anywhere. We might have to implement those tools, those lessons, in our own survival in these places. So I think some of it gets to, the next 20 years are where we start doing a lot of the genome engineering, some of which we've already talked about, and actually really monitoring it, perfecting it, understanding it better. And then I think some of the actual trials on humans that would actually be either temporarily or permanently genetically modified wouldn't be till the 2050s or 60s, because I'd want to have those multi-generational trials where we've learned at least from one generation that's passed and had a sense of if there's been any impact. And at that point, though, it's hopeful that, basically on Mars, it'll be either China or the US by the late 2030s. And that imagining people being on Mars by the end of the century is not too irrational. And then eventually there'd be, what I described as this, directed evolution and interplanetary exchange of knowledge, where you see a weird microbe on Mars, you sequence it, and then send the sequence data back to Earth. And then we could synthesize that organism where we have a lot more resources on Earth study it, understand it, maybe learn from it, and then send suggestions back to the crew on Mars and implement them. So in the next 100 years, more of in that phase is a lot of interplanet communication and back and forth. And the latter parts of the book, though, are getting out to the outer reach of the solar system, thinking about a generation ship, thinking about, when we get out 300 to 400 years. The whole goal of the 500-year plan is that by the time we get to 500 years from now, we would have enough knowledge and biomedical resources and preliminary data to be able to send a ship to another star. And so it's really all slated on what do we need to know in the next, basically at this point, 489 years to go to be able to have enough, I think, confidence that we could send people to another star and they'd get there and actually be able to survive. And so it is in the latter chapters, what exoplanets could we even send people to? So that was kind of fun to write, because just like human genetics were 20 years ago, that we only had one human genome and very little knowledge of other species. And now we have tens of thousands of them. And exoplanets, there were just a handful 20 years ago. And now there are thousands and thousands of them and more being found every day. Several hundred are likely habitable. So I talk a lot about how they're found in the later part of the book. And by the time we get to the year 2500, we will probably have, at this current rate, tens of thousands of candidate exoplanets that we could go to. And actually, one of my favorite parts of figures in the book is looking at where we found possibly habitable exoplanets. And if you see, there's one area where there's a big band of planets that we found. Some could be habitable, some probably not. But it's because it's only where we've been looking for the past really 6 or 7 years. We haven't even looked locally in our galactic neighborhood for the closest exoplanets. We've just started looking. And so towards the end of phase 7 and 8 is where I presume we'll have a large wealth of planets from which we could pick to send humans to. And then I talk a bit about also how do you entertain people if they're going to have 20 generations live and die on one spacecraft. What are the ethics of that, of sending a crew to their certain death? If you're the 5th generation, you wake up and you say, oh, well, I'm on this ship and I'll never be able to leave this ship, and I'm going towards a planet that I'll never see. To which it sounds bleak, but then it's really just a difference of scale, not of kind. Like right now on the Earth spaceship, we can't go to another planet. We can't leave this spaceship. We're stuck here. There's a lot to do on Earth, and it's my favorite planet by far. But it is just a difference of kind, a difference of degree, not a difference of kind.
We're stuck on a generation rock rather than a generation rocket.
Everyone's going to live and die on this rock, unless we figure out some way to go somewhere else. So And that I also describe as a sense of planetary liberty. When you have the ability to go between more than one planet, you've expanded the liberty quotient of a human being. So that's in a broad stroke. But there are 10 phases. They're broken down into 20 to 50 years. That's in a nutshell, kind of a quick summary of them. And the last phase is if we go further and further into the future and you think, okay, well, you go to one star, but then eventually that star is going to run out of fuel, the next one. And so the last chapter is focused on, you just go ad infinitum. And so, okay, if we keep going and going and going, do we just do this forever? Is this what our species does? Is we keep hopping around to find new suns? And I describe, I think that the deontogenic ethic applies, that if we're really facing the end of the universe, either the big rip or the big crunch or however it may end, and we face kind of the hardest and the final ethical question of, do we say we have the technology after 10 to the 100th power number of years to literally reshape the universe to prevent it from ending a certain way? Should we do that? Or do we let the universe die and have a new universe come that maybe life would emerge again, or maybe not? And if we don't think that life would come up again, I think we would still survive and protect life in this universe and maybe keep it. So it's kind of a fun to think about the cycling of universes and how many times has life emerged and then gone away again, or has it never done that? We just don't know, but it's interesting to think about. And that's the last chapter, which was kind of depressing to write, but I sent it to my editor. I said, I just finished the book. I finished the last chapter. It's about the end of the universe. I'm kind of sad. And he said, it's a long ways away. Don't worry about it. But it actually was kind of sad in a way.
It's very predictive. So I do want to, at some point, bring aliens into this. I'm a huge astrobiology nerd by trade.
Awesome.
And so I loved geeking out about all of the extremophiles that you talk about in your book. Deinococcus radiodurans is one of my favorite, actually. So I did immediately think about aliens, especially when you talk about this moral imperative to preserve life, specifically your kind of like shepherds of life theory, because you list this extinction awareness as the main reason that humanity should be the shepherds of life. But does that necessarily also include the ability to save it, to fix it? Because in my mind, if a greater civilization did exist and eventually did come and make contact with us, and explain beyond a reason of a doubt that we were in danger and we would wipe out life, at least locally on Earth. And it was a problem beyond our ability to solve. Does that give them this moral superiority to become the new shepherds and essentially help us help or force us to shape our evolution, right?
Unquestionably, I think is a
Okay.
consistent application of the ethical framework. Unquestionably, like that's also my hope. Is that, like, let's say it's a really advanced alien civilization that comes find us. Hopefully, they would subscribe to some of these principles of almost caretakers, guardians, rather than say destroying life and just absorbing it. But it depends on what we'd find. But I even describe in the book, like, what if it's an AI? What if it's some new computational system that is self-aware? And I say that I am one of the subject headings in the book is that I am matter agnostic towards cognition. So if it's silicon-based, carbon-based, if it's a creature, if it's made of meat or made of steel, whatever it is, as long as it has that forward-projecting consciousness and can understand extinction, this ethic applies to whomever or whatever that is. And so if they came in and they could solve something that we can't and said, this is the only way we'll be able to fix this, have you survive, they would have, I think, every right and a duty to actually help us and even potentially modify us. An analogy I give in the book is like, for example, there are I've been to the Panamanian rainforest, where there's extraordinary tribes who've lived the same way for thousands and thousands of years in the remote rainforest. And they're let's say they stay just as they are for another million years, 10 million years, and it gets longer and longer, and for some reason the climate never changes there because it's near the equator. Eventually, though, they have to leave. If they stay there, it is suicide. So it's like, even as much as we don't want to disturb cultures and we want to preserve life and preserve cultures, at some point, if you're burned to a cinder, then you have no culture. So at some point, the preservation of any valued entity in the universe requires likely movement from the planet. And so again, it's a long ways away, but it's inevitable. And so I think if some creature came to us and said, listen, you guys aren't going to make it out of here, but we can help, I would be very happy with that.
Yeah, in a kind of unfortunate way to prevent these cultures and knowledge from falling to entropy, you do have to insert order and kind of conform eventually, right?
At some point. And it is, which brings up colonialism and exploitation, a lot of really, awful harms of human history. But in this case, it's flipping it around. Like, instead of actually going in to try and exploit resources, the explicit goal is to preserve them, which isn't always interpreted that way. Even if some of the people in the 1700s who went to try and preserve cultures, there were a handful, but they were not. They didn't. They were overwhelmed by the people that were doing harm. And so I think you have to make sure that it's done, correctly and with the true goal of preservation.
Yeah.
Now, one piece of biotechnology on the focus of those different stages that are somewhat medium near-term future is the idea of unnatural base pairs. This was just a really fascinating section of the book to read because it's, we're given with our DNA A's, C's, G's, and T's to build with, but the possibility of inserting 4 new base pairs and the complexity that can build from that. And additionally, one topic that Nick and I have discussed is a Martian parasite, if you will, that if we somehow bring life to Mars, well, then it starts mutating. We then bring a pathogen back to Earth. As you said, if we're sending samples back and forth, that can risk, a pandemic, but a multi-Pangea, right? Multiple planets all being infected now. How does unnatural base pairs fit into that discussion and hopefully protect us as we start to expand humanity's reach?
Yeah, great questions. Yeah, and I describe it a little bit in the book of some what if scenarios. There and like with any technology, it can be either a tool or a weapon. This is true for swords, for fire, for nuclear energy, which could be either a bomb or a source of power. Same goes with genetic engineering and even what are often called xenonucleic acids, or like alien nucleic acids, which just means they're not the standard 4 bases, or 5 if you include uracil and RNA. And they're just slightly different. So you can have different base pairing systems, different adaptations to new environments. And one way you could avoid risk of planetary contamination is to have only things that you're on Mars be done with bases that don't exist on Earth, as one way to keep it contained, because then they don't have a substrate on Earth that they could use. But that would require a lot of engineering and work, and wouldn't necessarily actually be functional. But I think there's something that's a risk that we'll have to keep an eye on. As you've probably heard, there's going to be the Perseverance samples. The Perseverance rover is collecting samples on Mars as we speak, and is going to bring them back probably by 2032. There's discussions within NASA. Should we have like a BSL level 5 facility? So currently the highest biosafety level lab is 4, which is used for like, Ebola, or in some cases,
Anthrax, yeah.
anthrax. And what if we need to have like a city that's in a big dome and then put a BSL-4 lab inside that just in case? It is an active discussion at NASA because, just what if? Because the moon has almost no water and is pretty sterile. It's probably not a high risk, but we know Mars had lots of water at one point, may have had life. What if it's dangerous? So we hope not. But I think the xenonucleic acids give you a way to potentially avoid that, or at least to limit any risk if you deploy them.
Throughout your book, you talk about all these fantastic technologies. And so, of course, we're going to let the audience read the book and enjoy some of these discussions, how they all build on top of each other. I was looking to wrap up with one last question of what advice would you give someone wanting to work in the human spaceflight project, potentially on the genomics, genetics side like you?
I think what's great is there are a lot of resources today that didn't really exist 10 years ago or 5 years ago that can help in this. So in the science fiction space, there's a lot of great books from like the Expanse series, and there's also a great show on Netflix that shows it to get you thinking about it. Seven Eves was a recent book by Neil Stephenson, which I really enjoyed for reading. But for actually getting involved, it's really easy to jump in and start to get your hands into the data of human cells or human tissues or mice or worms that have flown into space, and play with the data at the genetic level or molecular level, how they changed when they went to space. There's a project at NASA called Gene Lab, which is built on open science for all in space. So people want to look at what happens to when you go to space. How do you understand it? What are some of the mission parameters? And you can get your hands dirty, get into playing with the data, help write papers, meet other scientists at NASA, or people who collaborate with them, like myself. And if you say I want to help analyze some data and build code and dive deep into some samples that got dissected in space, a lot of them are public, and you can play with the data and work with investigators. And then if you want to do analog missions, there's ways to say I want to go to a remote facility and be like a pseudo astronaut for 2 weeks to learn about it. That's an option. There's also a lot of it is in the Gene, like I mentioned, the Gene Lab website at NASA, but then also a lot of the mission details are all public. And also SpaceX and Axiom are two private space companies really engaging the public a lot. And so they're also taking in interns and fellows as well. So it's a lot of back and forth and a lot of opportunities today.
Well, fantastic. Where's the best place for people to go to find your book? We'll include links, but where's the best place to help you find those books?
For the next 500 years, you can just go to, if you just Google it, there's an MIT Press page. I have a lab page. It's just masonlab.net. And on Twitter, it's @Mason_lab. There's a lot of details there. My Twitter feed is kind of a collection of papers I'm reading or random thoughts I have in my head. And then, a lot
as
of
it
the
should be.
Yeah, exactly. And Instagram has a little bit of that too. So that's just Christopher.e.Mason. And also, if you want to, even like things like Jet Propulsion Laboratory, it's funded by taxpayers. So if you're a U.S. taxpayer, go take a tour sometime. They really encourage tours and visitors from Johnson Space Center, Jet Propulsion Laboratory. Think of the places that people go. Ames Research Center. So if you're in the U.S. and you're a citizen, it's easy. If you're not a citizen, there's just more paperwork. But you should go check them out if you're here.
All right. I have one last question, very quick. I know that you're a huge fan of Isaac Asimov, and you even use his quote in your book. I believe it is, "Never let your sense of morals prevent you from doing what is right." So being someone who is both super invested in space and the future, also being the director of the World Quant Initiative for quantitative prediction, did you kind of feel a little bit like Hari Seldon when you were writing out this 500-year plan, like making this prediction for what humans need to do to avoid the inevitable end, or at least to soften the blow, right?
It's a good. I didn't. It's a good question. There's now recently a series on Apple TV that is
It's very good. I've been watching it. Yeah.
Dramatic viewing of the Foundation series, and I didn't feel so much like Hari Seldon because I don't feel it's actually in some sense. I felt a little bit of the ghost of Hari Seldon, but but flipped around. Instead of he was really forecasting an imminent doom. I think I forecast a really expansive and much more broad future that's possible. So maybe it's the beginning of the galactic empire rather than the end. I'd say
There it is.
so. Um, but it is of a similar line where you think if we do the science and the math and the engineering correctly, this is all possible, and it's more what I view as a hopeful fate rather than just a dream. So I think it's a treatise of hope and likely path ahead rather than just a collection of rando ideas.
Well, Dr. Mason, thank you so much for agreeing to come on and talk to us. We both loved your book. I think we have been super excited to get the chance to meet you and get to talk to you about all of this. So we have your resources. Thank you so much. To anyone listening, of course, we will also post his Instagram and social media and the lab pages along with this when it is posted. So thank you so much for coming out here and being a guest here. Dominic, do you have any final words or questions?
Just the sign off that we agreed on for everyone: stay oxygenated.
Yes.
Great. Thank you all. It's a pleasure to be here. Thanks.
Thank you.